Good morning, everyone. We'll start in a few moments. All right, so I think we'll be ready to start. So, good morning. So, on today's menu, what we'll wrap up what we'll see this semester about quantum mechanics. A lot of material has been cut due to the necessary changes to continue the semester. And next, we should be able to start the second part of modern physics, in which we'll see nuclear physics. On quantum mechanics, what we still need to see is the concept of energy levels, which you already have covered somewhat, at least in chemistry. They are approximately the same thing as orbitals, as you have seen. So we'll see how these are linked to the electrons. And unlike what you have done, we won't postulate their existence, but we will explain why atoms have energy levels. Why does it make sense for them to have them? And last, we'll go from this general concept of energy levels and apply them to a specific atom, the hydrogen atom, using Bohr models. Again, I won't really explain the model itself. I'll explain it. It's just we won't use the same postulate Bohr had to make. We'll use our own deductions to start with, then find give an expression for the energy of all of the levels, and then the formalism will be more or less the same as for general atoms. Before we move on to this, I think we should have a short discussion based on what was on the title screen and what we discussed last time. So last time we discussed about the photoelectric effect and how diffraction was observed in the case of electrons. In each of these two cases, for instance, for the photoelectric effect, this led us to say that light behaved as a wave whenever it traveled, and as a particle whenever it was absorbed, whenever it interacted with something. And the same thing with the electrons. They interacted with the screen as particles, as we are used to treat them, but whenever they traveled as waves. And we called this behavior the wave-particle duality. Normally, I spend a little bit more time on this, so here it will just be a short discussion on matter. What does this mean, actually, for light? And mostly, I'll focus most of the discussion on matter. What does it mean for matter uh, to behave as a wave, and why don't we see it at our scale? To do this, I'll have to go back on the short. Isn't it open? Okay, here it is. On the short demonstration I had done with the thought experiment with the interference of an electron going through two slits. So we had two slits, a screen on which I forgot to make the transition. Two slits, a screen, a dot which represents an electron, and I had a wave-like pattern which I represented to show where more electrons were detected. So for instance, if we did the experiment once, we sent an electron from the left and then saw where it ended up on the screen. Sometimes it was found here, some other times it was found here, some other times here, another time might be a little bit more toward the center, like before. And as we did the experiment a bunch of times, we could bring all the results together to get a sense of where we detected more or less electrons. So here I'll just add a few. Hope the periodicity fits, otherwise I'll just cry it all. Looks like I'll have to cry. Okay, bring this towards the center. So we're about to have an idea of, if we repeat the experiment a bunch of times, where we'll have more electrons, where we'll have less electrons, using the formalism of interference, like we have seen for light. But we're not able, for a single experiment, to predict where the electron will end up. I'll remove most of them just to for the discussion. So if I were to do the experiment once, and I focus on just the areas in which I have the if I say this, I kind of spoil the thing. Well, I'll have to say it, where I have the highest probability of getting an electron. So let's say I could do the experiment and measure an electron right in the middle of the pattern. I could do it also, and instead get an electron over here. I could do it another time, get an electron over here. I cannot predict where a single electron will end up. But what we do know is the probability of where, the probability, depending on where we're looking at the screen, where the electron will be measured. Unlike classical physics, quantum mechanics is non-deterministic. You do not know in advance what will happen. So even if you have all the information in the world about the particle you are sending, the electron I'm sending from the left, you can't predict exactly where it ends up on the screen. And the other way around, if you know the state of the particle at a given time, like where it ended up, you can't go back in time using a bunch of laws and know its past states. It is random with a probability linked to the wave function of the particle. And that is the sense we give to the wave function of particles. They are linked, at least their amplitude is linked to the probability. The higher the amplitude, like here we had a resulting wave with constructive interference, a greater amplitude, we have a high probability. And whenever the amplitude crashes to zero, we have a zero probability. And in between, we have some non-zero probability of measuring an electron there, but still less likely than at a place where we have perfect constructive interference. So the sense of wave-particle duality is that as long as you don't make a measurement, like you don't have a screen where electrons will come and crash, the position of the electrons are not determined. You have a given probability associated with a position, but their exact location is not determined in advance. That's the sense of the wave-particle duality. A measurement, a measurement determines the characteristics of the particle you're looking at. And this is linked to why we cannot see the effects of quantum mechanics, most precisely of the wave-like nature of particles at our scales. At our scale, like about every object around you, like the desk I have in front of me, my own body, the chair I'm sitting on, are made of a lot of particles. And these particles are constantly interacting with each other. So they are constantly, for instance, colliding with each other, which makes their position determined and destroys the wave-like behavior, the probability, everything that is linked to their position not being determined in advance is destroyed because they keep interacting together, they keep colliding, like here when an electron was detected on the screen, they keep interacting together. In general, in quantum mechanics, interactions are our worst enemy, which is why you also observe it at very small scales where there are a lot less interactions at once. There is also a second condition which makes some characteristics specific to quantum mechanics appear, which we'll discuss uh, in the presentation when we'll talk about energy levels. So the discussion we just had was more or less for closure. I do not expect. Well, I won't ask questions on it. It's more to explain a little bit more what it means, and so if some of you have some particular interest, to give you some more information. I remember Jonathan reading at least having a book on quantum mechanics about a year ago in Science on Tourne. So I thought maybe this would be of some interest, at least to you. Next, for the energy levels. Knowing from what we've seen, mostly in the first part of the course and what we just discussed for the diffraction of electrons, we'll be able to deduce why atoms have energy levels. So for this, we'll go back to February, was it? When we studied standing waves. So if you remember, a standing wave was created by two traveling waves interacting with each other. They were going, in our specific case, in opposite directions. And then we took a look at, if I focus on a wire, at a specific case where both ends, and I forgot again to make the transition, where both ends were tied to a wall, they were fixed so that they could not move at all. And we call these locations nodes. Whenever we did this, the wave, which at first could have any given frequency, changed its properties. Only a very few specific discrete, which is the inverse of continuous. You cannot give it a real value, just an integer times something. Can only have some specific values of the frequency, which were given by the equation we worked with a bit a few months ago. Whenever we put what we'll call boundary conditions, that we stated that both ends had to be fixed, we went from a case where the frequency could take any value to a case where it could only take discrete values, just a specific set of values. What we had discussed? Well, through diffraction interference experiments, we saw that what the experiment result could only be explained if the electron, at least in some part, behaved as a wave when it travels. So, all right, it behaves as a wave. Let's see if we can find some boundary conditions for it. Well, the electron is usually, at least often, linked to an atom. So you have a nucleus, a huge positively charged body nearby him. And these charges attract each other. So due to this attraction, the electron is usually trapped near the nucleus. It cannot move very far away. It has a similar effect to preventing it from moving far by putting boundaries on the outside of the atom. So it is, again, a soft, not a hard boundary, but a kind of soft boundary for the wave of the electron. It keeps it under in a specific location. The wave cannot go outside. We fix that the wave must have a node outside of the atom. So again, this acts as a boundary condition for an object which we have seen behaves as a wave. And this will have the effect that, like in a standing wave where its frequency took discrete values, the properties of the electron will also take discrete values, such as its angular momentum and its energy. So what we call energy levels are, in fact, the discrete possible energy values of energy that an electron can have when bound to an atom. And since, well, when you change the element, when you go from hydrogen to helium to oxygen and so on, the nucleus changes. So the pull that the nucleus has on the nearby electrons also changes. There are also the electron cloud around it that changes based on the atom you're looking at. So the repulsion and attraction change depending on the element. So the boundary conditions change based on this, which in turn changes the possible values of energy that an electron can have, which is why for different atoms, you have different values for the energy levels, different possible orbitals. So in fact, due to this fact that the nucleus pulls on the electron, and that the electron behaves as a wave, it would not make any sense for the electron to be able to have any kind of energy inside of the atom. While inside of it, it must have discrete energy. But while it is free elsewhere, when it is not bound to nucleus, it can have any energy it wants. We do not have energy levels outside of the atom. Same thing also whenever similar whenever you are looking at an object around you. It does not have discrete energy levels because it is not, in general at least, bound to another object. And the representation we can make using the wave formalism of these levels and the wave associated with it is using the formalism is introduced by De Broglie. De Broglie he's the one who had first worked on trying to treat particles as waves. And one way he represented the thing was if, let's say, you had some nucleus at the center and you imagined a circle around. So I'm looking at the dotted line, a circle around this nucleus. You can take the wave of the electron with its De Broglie wavelength and wrap it around the circle. And if you want it to go back on itself, you have a bunch of possibilities. You can wrap it 1 time, 2 times, 3 times. Here I represented a total of 7 times. I'll start here to represent it. So I'll count the number of wavelength I wrapped around the circle. 1, 2, 3, 4, 5, 6, 7. So whenever you talked about n orbitals, which had a spherical shape around an atom, the more, you had the first one, the second, the third, the fourth, they had increasing radii. Is that how it's pronounced? Radii, I guess that's how it is. They had increasing radii because the more you consider an orbital with a greater index, the more wavelength of the electron you wrap around it. So it is a way to represent the orbitals. Again, not so important. You have a clearer figure also in your textbook. I listed here with not only one example, but I think they represented 3 different orbitals using this. The more diagrammatic way we'll represent them is usually just with an axis of the energy and a bunch of lines to represent all of the levels in increasing order. So we will have some levels, some orbitals with a lower energy and some other with higher ones. Here I put 3 dotted lines because they keep adding up until you reach the highest energy of the atom. So here I have the axis of the energy. Here I put indices to explain what each level is. And here I represented as a red circle an electron. So in an atom, since the energy levels are the values of the energy, the only allowed values of the energy that an electron can have, will always have to represent an electron on them. Never between 2. That would mean that it would have a forbidden value of energy. And the name we give to them are the following. The very first one, the one which represents the lowest energy in an atom, we'll call the ground level. And all of the others above will be called excited levels, excited states sometimes, but the main thing, ground level, excited level. Excited because we'll need some energy for the poor electron here that is stuck at the bottom to reach them. There are a bunch of possibilities to give energy to an electron. It can collide with other electrons, or more often, and what we'll consider here, if light is shining on the object, light, as we discussed, will interact with the electron in the form of a photon, which will be absorbed and give energy to the electron. So if you send a photon, here I'll talk in a second about the conditions that the photon must respect. If you send a light on it, the electron will be able to jump from one level to another. So if the photon carries just a little bit of energy, the electron might just jump one level, here jump two. If the photon has more energy, might jump even higher. And if we have very high energy photons, we might even go back to the case we studied in the photoelectric effect, where the electron is ripped off of the material, doesn't even go on energy level, but outside of the atom. So by absorbing light, the electron can go to a higher energy level. And the opposite case, whenever it wants to drop to a lower energy level, it has to get rid of the energy it has in order to do so, in order to go back to a lower energy. So it gets rid of this energy by emitting a photon. And as we discussed, what is not allowed is for the electron to end up between two levels. It cannot have this energy. So if, okay, this is, one second. This is not the one. All right. Let's hope it doesn't happen again. So if a photon that were to be absorbed would make it so the electron would end up between two levels, but that is not allowed. The electron cannot end up there, so the photon won't be absorbed. And again, the electron cannot start there and go back to another lower energy levels. So we'll only have some specific energies of the photon that will be absorbed and emitted, which correspond to the difference between two energy levels. So the energy of the photon that can be absorbed by a given electron has to always be given by the difference between energy of two levels. I put absolute value to take care in one single package of whether it is absorbed or emitted. So in one of these two, one of the energies will be higher than the other. It doesn't matter due to the absolute value. And we know that the energy of a photon is linked to its frequency through the Planck constant. So the Planck constant times the frequency gives us the energy of the photon. So if we have some condition on the energy of the photon, only some energies can be emitted or absorbed. It means that only some frequencies can be emitted or absorbed, and thus only some wavelengths. Which is why, through spectroscopy, whenever we have an atom that we excited before emits light, and we gather this light, we obtain a bunch of fringes of different color, which allows us to identify the atom. That is because the wavelengths that we'll detect depend through this. So the wavelength affects the frequency, which affects the energy of the photon, which comes from the different energy levels, which come from the energy level themselves. This is why it enables us to identify elements. Since the energy levels vary depending on the atom, the wavelength we gather from the light being emitted by this atom will also vary because of this. This is why this is a good tool to identify atoms. So one last remark. So as stated before, this condition that only some values of the energy of the photons can be absorbed is only valid whenever the electron jumps from one level to another. In the photoelectric effect, we did not have such a condition. The electron could absorb a given photon as long as the electron was freed. There was no further condition. That is because the electron does not end up in a level whenever it is freed. So we do not have this condition in this case. So this condition only applies when we have a jump between two levels. So on the general concept of energy levels, where they come from, and how to have transitions between energy levels. Will you have some questions so far before we start discussing Bohr's model more specifically? As always, please don't hesitate to write them down. If you feel like it will be long to type, then you can quickly type question, and I will know that I will have to wait for you to finish typing before moving on. So, most atoms can be fairly complex. You will have a bunch of protons, a bunch of neutrons, and a lot of electrons around them. So the first case that was studied was the hydrogen atom, mainly because it was simpler, so it was a very good first step. We only have one proton and one electron around it. Here it is. So I presented a huge proton with a small electron around it. So pretty much the simplest case we can study. The model that was first used to describe it was developed by Niels Bohr, a Danish scientist. And he built what we'll call a semi-classical model to explain it. What I mean by semi-classical is when he developed it, the wave-like properties of matter were not yet discovered. So the way he imagined the hydrogen atom was having a proton at the center with a small ball-like electron orbiting around it. So he imagined a ball as an electron moving through space on a circular path. And he postulated that there were a bunch of spherical orbits around the proton that were allowed, and the electron could not be between two orbits. So this sounds very similar to our idea that an electron cannot end up between two energy levels because that is not energy that is allowed whenever it has boundary conditions. He also postulated that the angular momentum was quantized. So quantized is what we use to say that it takes discrete values. And also, he had to make a postulate that whenever the electron was orbiting the proton, it didn't lose energy. This was a huge contradiction with the electromagnetic theory that said that whenever a charged particle was under acceleration, and a particle going a circle is under constant acceleration towards the center of the circle. It emitted light. It emitted energy. So if Bohr did not make this postulate, that would have meant that the electron would constantly give off energy, so lose energy, and go closer and closer to the nucleus until it crashed on it. And it could be shown that under a second, the universe as we know it should have ended. Obviously, that is not the case. So the electron did not go and crash on the surface. So because he conceived the electron as a small ball, he has to postulate this. But from our point of view, it is because the electron is not orbiting around the atom. It is not a small ball moving through space. It's just a wave which has some probability to exist in a given space. If Guillaume has given you general chemistry in your first year, he probably said that there is a given space in which we have like 90% chance of finding the electron, and with 10% we don't know where it is. That is the sense of it. So due to the wave function, and we have a part where its amplitude is the greatest, and the outside is a lot lower. The greatest part 90%, the outside 10%. The electron is not orbiting, so we do not contradict the electromagnetic theory. And his model worked very well with atoms that had a single electron, but since he developed it precisely when there were no interaction between two electrons, it didn't work so great with atoms that had more than one electron because it was not designed to do so. In your textbook, there is a pretty long demonstration. I find it interesting, but it won't be very much important for what we'll do. To find the value of the energies of each of the levels in the hydrogen atom. So the same representation we had before, the hydrogen, even though it has a single electron, has a whole lot of possible energies. And these energies take the form in electron volt, like this, minus 13.6 electron volt times 1 over n squared, n being the index of the level, so 1 for the ground level, 2, 3, 4, and so on for the excited ones. Negative, due to the same reason as when we discussed the photoelectric effect, whenever it is bound, we will take the electron as having a negative energy, and whenever it is free, a positive one. So the negative comes from this. And since whenever we have more protons in the nucleus, the attraction is greater. If we consider some other nucleus with more than one proton, but again a single electron, we can still adapt Bohr's model to have a similar form, except to have the impact of the new number of protons, Z here being this number. So this again works with the case of the hydrogen, where we have a single proton. If we have a single proton, Z is equal to 1, so we have 1 squared is equal to 1. This is consistent. So keep in mind that these are in electron volts. And also something else I had to say. Yes, about the other nuclei that can correspond to this. In a neutral atom, the only one that exists with one proton is hydrogen, so all of the others will have to be ions, off of which some electrons were ripped off. This is possible. We can extract electrons from an atom, so this will only work whenever we have ions. Before we do an example on how to treat energy levels and the transitions between them, would you have a question to ask, a comment to make? Otherwise, the real last thing I have for example is a picture you may be seeing as my background. As scientists, mostly chemists and physicists, developed all the theory of quantum mechanics, they had to meet, obviously, to discuss things, share ideas, share results of experiments, new theories, and so on. So there were a bunch of conferences organized to discuss this, such as the very famous Solvay conference held in 1927 in Brussels, in the Netherlands. So on this picture, you have pretty much the all-star team of chemistry and physics of the beginning of the 19th century. You might recognize, for instance, this gentleman in the center, Einstein himself, as well as a bunch of other people, which you may or may not know depending on what you have seen so far. For instance, you have Bohr is where is he again? Where is he again? Here. You have Niels Bohr over here. If you have heard a little bit about relativity, there is Lorentz that is over here. Curie, Planck we have not seen because I skipped over the black body, but he is here. Other names you might have heard if you have seen some or read something about quantum mechanics. You have Schrödinger, which is this gentleman, as well Heisenberg. Heisenberg is over here with his uncertainty principle, which unfortunately we could not cover this year. So, what I suggest, I take about 3 minutes to arrange my setup so I'm ready to do an example. And then we'll take a look at example 9.15 of your textbook. So I'll see you in a few minutes to arrange this. We'll start again in about a minute. As stated, we'll take a look at example 39.5. If you have your textbook nearby, it is on page 1292. I'll just write where we are. Example 39.5. In which we'll work with energy levels. Not in the specific case of the hydrogen atom, but the principle is the same. In here we'll be given some values of the energy of the levels. In the case of an hydrogen atom or another atom with one single electron, you just have to use the equation we saw to find the energy of the levels you will need. So here we'll consider an atom with 3 energy levels, one of 0 electron volt. Here they put them positive, it doesn't really matter. The one with, I'll call it E1, with E1 being 0 electron volts. Another at 1, another at 3. E2, E3. The energy levels do not have to be equally spaced. In fact, in general, they are not. And we want to know what are the frequencies and wavelength of the spectral lines this atom can emit when excited, and what are the wavelength this atom can absorb when it is in its ground level. I suggest we start with B, actually. It'll be a bit simpler. In A, we'll have some other nuance. So we'll start with an electron in the ground level. So this will be our electron. Now, it will absorb light whenever the energy of the photon enables it to jump to one of the other levels. So here we'll have this transition and this one. It can possibly occur. So what we'll have to do, find the energy of the photon needed for this transition, find the wavelength and frequency. Same thing for here. So, first transition from 1 to 2. We'll find the energy of the photon that we need to bring the electron from the ground level to this particular level. So it corresponds to the difference between the two energies. So how much we need to jump. So we have, well, this is 1 minus 0, big deal, 1 electron volt. So we need a photon with this energy, but we also know that the energy of a photon is given by the Planck constant times the frequency. So here again, two paths. I could use the Planck constant in electron volts times second, use directly this value of the energy, find the frequency. Or I could also transfer this into joules, then use the value of the Planck constant in joule times second. Both work. I'll transfer this into joules. So the energy of the photon, which was 1 electron volt. Again, electron volt, you just have to read it in the dumbest possible way. It is the E, the elementary charge, times 1 volt. So whenever you want to transfer it, it is equal to a factor of conversion equal to the elementary charge. By using this, well, we'll have the energy of the photon, which is just equal to 1.602 times 10 to the minus 19 joule. And now using this, we can find the frequency as the energy over the Planck constant, which is thus equal to the energy we just found over the Planck constant, 6.626 times 10 to the minus 34 in joule times seconds. If I take a look at just the factor 10 minus something, this will give me 10 to the plus 15. 34 minus 19 is 15. And for the rest, .24, let's say 2. This is in hertz since I had 1/seconds. So we have the frequency, and for the wavelength, well, the wavelength is linked to the frequency through the speed of the wave. Here, the speed of light. So we have c is equal to lambda f, and thus the wavelength is equal to c over the frequency. C being the speed of light in vacuum. This is 3 times 10 to the power 8 over what we found, times 10 to the power 15. So 8 minus 15 is minus 7. And 3 over what we had, 12.4 times 10 to minus 7 meters. For the other transition, we'll have a different wavelength. The principle is the following. So we considered this transition for the other from here to here. The energy of the photon, 1, 2, 3. The photon is again given by the difference between the energy of these two levels. It is the energy needed to jump from the ground level to the third excited level. It is equal to 3 minus 0, 2 electron volts. And using this energy, we'd go through the same pattern, transfer it into joule, then find the frequency, then with the link we have through the speed of light, find the wavelength. So for each different transition, the main difference will be the new energy of the photon will have. What we wanted in A was a bit different. So in B, we wanted to find the wavelength that would be absorbed when we had an electron at the ground level. In A, we start off whenever the electron is already excited, so already at a higher energy level, and it wants to drop down. Eventually, all electrons drop down to the ground level. The time they spend on a higher energy level is usually pretty short. So we want to find the frequencies and wavelength. So whenever the electron is excited to a higher energy level, here we have two different possibilities. It can either be on the level we referred to as having energy E2, or second case, it could be on the very highest level. I forgot to draw the electron. Here it is. If I start over there, again, like we did, we first have to find, well, what are the possible transitions we can have? And from there, we'll be able to find the energy of the photon. Well, if it is in this level, it can drop down by one level, or it could drop down by two. These are the two possible transitions you can have from there. And let's say if we take the case where it jumped from here directly to the ground level, once there, it is at the lowest possible energy. It can't go any lower. But if instead it goes to this level, but from there it still has room to go down a little bit more. So if it ends up on this level, it can then again go back down by one level. So there are three different transitions we can have. So we'll have three different energies of a photon being emitted that we can detect, three different frequencies, three different wavelengths. So if we were, for instance, to study the emission spectrum of this atom, we'd get three bands in our spectroscopy experiment. So each in turn, again, I'll do the first one, the other two, I'll just highlight the energy of the level, and the rest will be the same. So which one do I do? I'll do this one, since this was not a transition that was possible whenever the electron was in the ground level. So I'll first consider when the electron jumps from the very highest level, will it be possible for the electron to go from E2 to E3? Well, yes, but it would have to absorb a photon to do this. But yes, it is possible. If the electron was here and a photon came by with just the right energy to bring the electron back up, would be possible. Absolutely. We didn't consider it in the last number since it was specified to us that the electron was on the ground level, but indeed, it is possible. Thank you for the question. So we'll study the light that is being emitted when the electron comes from this level to this one. So the inverse transition of the one Jean suggested, it would have the same energy of the photon. The energy of the photon will be the difference between the two. Earlier, did I write 3 minus 0 was equal to 2? I did, didn't I? Sorry, this was a 3. This was a 3. Better. All right. So we have E3 minus E2, which is 3 electron volts minus a single one. So we'd have a photon with 2 electron volts. Through this, this would mean that in joule, this is in joule, we'd have 2 times this, so 3.204 times 10 to the power minus 19 joule. From there, same principle as we did before. This is the photon that is emitted through this relaxation, through this transition to a lower level. So we can find the frequency of this photon. The frequency of the photon is the energy over the Planck constant. We know both these quantities. This is 3.204 times 10 to the power minus 19. This is 6.626 times 10 to the power minus 34. we should get twice the value we had before, since the energy of the photon is twice what we had in B. We'll have 0.484 times 10 to the power 15 hertz. And from there, again, we can find the wavelength. C is equal to lambda times frequency. So the wavelength is C over F 3 times 10 to the power 8 over our answer. Again, we'll have something times 10 to the power minus 7. So again, because I rounded, I might be less precise, but it should be 6.198 meters. And for the other transitions, again, the only difference is the energy of the photon. So from here to here, the energy of the photon would have E3 minus E1. From here to here, it would be E2 minus E1. So that is the only difference. From there, the principle is the same. So from this, on how to deal with energy levels, how to find the frequencies and wavelength that we would detect in a spectroscopy experiment due to these transitions. Would you have some questions or comments? Otherwise, that would bring us to the end of our study of quantum mechanics. Mainly, we saw that both light and matter cannot be taken as just a wave or just a particle. They behave as a little bit of both, depending on the context. This led us to deduce the existence of energy levels due to the wave-like nature of electrons. And in these transitions between levels, photons are absorbed and emitted if they enable an allowed transition. So the electron starts at an energy where it can exist and ends up again at an energy at which it can exist. So I take again, probably I hope this time for real, about 3 minutes just to change my setup back, and then we'll start the last bit, nuclear physics, just a little bit. So I'll see you in just a few minutes. It'll be written 5 minutes. My keyboard is a bit farther right now due to my setup, but it is actually 3. So, shouldn't be All right. So the last part of modern physics will be on nuclear physics. Nuclear physics being the study of the nuclei, so the center of the atoms. So, well, I explained my setup in a few seconds. I read whatever right now while I set up the rest. So, the study of the nucleus of the atom. In this, much like in the case of quantum mechanics, you will have to let go of one assumption you had made before. So, in the case of quantum mechanics, we had to let go of the fact that some objects behave purely as wave or purely uh, as particles, but it depended on the context. They could depend on they could behave as a bit of both. In this one, you saw previously. Sorry, I'm just doing two things at the same time, so I'm just a bit confused. In this one, you saw previously three main conservation laws, three quantities that were conserved no matter what you did. The first, I'll try to get the mirror. All right. You saw with Luc the conservation of energy. You cannot end up with more or less energy than what you started with. For instance, it can transform, can go from kinetic to potential to something else, but the total of it has to remain the same. Then, in the middle, mass, which you saw in chemistry. Since you cannot create either, you cannot create or destroy matter, you should always have the same amount of mass at the beginning of a reaction as you had at the end. And last, the conservation of momentum, both linear and angular, which tells you, which you had to use in order to solve collision problems, and which is pretty useful in particle physics. In a few minutes, only two of these pillars will be left standing, and the third one, unfortunately, will have to collapse. All right, should be fine. If there are some problems, I apologize in advance. So our study of nuclear physics will go as follows. First, we'll see what binds all of the constituents of the nucleus. For this, we'll have to briefly review one of the results of relativity. We won't demonstrate it, we'll just discuss around it what it means. Then we'll discuss how nuclei decay over time, how they behave in reactions. So we'll discuss the topic of radioactivity, as well as the rate at which this radioactivity happens. And then we'll have a short discussion on two main types of nuclear reaction, fission and fusion. First, so as stated, nuclear physics is the study of the nucleus of the atom. So a nucleus is made mostly of two types of particles, neutrons and protons. Protons being positively charged, neutrons being non-negatively, being neutral in charge. In general, when we will talk about a given nucleus, or as it will sometimes be called, a nuclide, we'll use the following notation. We'll put X here to specify the element. For instance, if we were talking about oxygen, this would be an O. If we would be talking about calcium, this would be Ca. And we'll put in superscript and subscript two quantities. First, in subscript, we'll put Z, which is the number of protons this nucleus contains, and A, the total number of what we'll call nucleons inside the nucleus. A nucleon is a general name we'll give to a particle inside the nucleus. It encompasses both neutrons and protons. So whenever we call A the number of nucleons, it is the sum of number of protons and neutrons, n being defined as the number of neutrons. What defines the element whenever you, for instance, know that you have hydrogen? This comes from the number of protons. So for hydrogen, you have a single proton. For helium, you have two. For whatever comes next, calcium, is it? You have three. For oxygen, you have five. Carbon, you have six. So it is determined by the number of protons. But even with a given number of protons, for the same element, you may have a different number of neutrons. For each configuration of a given element with a different number of neutrons, we'll call it an isotope. It will still have, at least from a chemical point of view, about the same properties, but won't have the same nucleus. In general, we'll name it after the number of nucleons. For instance, later, probably next week or maybe tomorrow, we'll see. We'll, for instance, talk about carbon 14, carbon 12. The number we put at the end is the number of nucleons. So it tells us how many neutrons plus protons are in there. Same thing for helium. We'll sometimes speak about helium-4, helium-3. This refers to how many nucleons. Helium-4 has 4 nucleons, 2 neutrons and 2 protons. Helium-3 has 2 protons, but a single neutron. But if you try to jam together a whole bunch of positively charged particles, electromagnetism tells us that it is not a good plan. These particles repel each other. So whenever we try to put them together, we'll most likely end up with something very unstable. Which is why we need a new force. In order to explain this, gravity is not large enough to counter this effect. The new type of force we'll need, which will be an attractive force to enable the nucleus to stay together and not break apart as soon as it is formed, we'll call the nuclear force. It is a force that is only very large at very, very short distances. So whenever two particles are very far apart, it will be negligible, which is why we did not treat it so far. But whenever they are very, very close to each other, such as in the same nucleus, or even the same nucleus close to each other in the same nucleus, in very large ones, it won't apply to two nucleons on opposite sides of the nucleus. It will be stronger than the electromagnetic force, and we'll be able to counter it. So here I drew a small graph of the potential energy as a function of the distance between two nucleons. Whenever they are zero, that means that they are about at the same place, so very, very close to each other. So what it means to have a strong attractive force, it means that it is energetically viable for two particles to be close to each other. So they should have a low energy. Particles tends to rush to a low energy state. So as you start with two nucleons very far, pretty far apart. First, here I drew it for protons. It'd be hard to read them together because of the repulsion, because they are both positive. But at some point, the nuclear force will start to get stronger and stronger until it is stronger than the repulsion, and it will be energetically viable for the nucleons to be close together. This will present with what we'll call a binding energy, an energy that the nucleons will have that, well, as the name implies, binds them together. This energy will have a pretty odd origin, which I will need to introduce some new principle to explain. First, some introduction based on this. Last semester in your course on electromagnetism, you studied the effect of the electric field and magnetic field on some charged particles, and you probably in exercises or even on the exam took a look at an alpha particle. An alpha particle is a nucleus of helium-4, which is made of two neutrons and two protons, which is why you use the charge for it of 2 times the charge of a proton, so 2 times the elementary charge. But if you ever tried, you may have noticed that if you compare the mass that was provided to you for the alpha particle, and if you compare it to the mass of the neutron and the proton, if you add 2 times the mass of the neutrons and 2 times the mass of a proton together, you don't get the mass of the alpha particle. In general, whenever we deal, especially when we deal with huge energies, mass, unfortunately, is not conserved. You can create and destroy mass, as we'll see, through the mass energy equivalence principle. In fact, mass alone by itself is in general not conserved, but it is not a pillar by itself, but part of another pillar, the one on energy. Probably the most famous equation in physics, E equals mc squared. We are finally ready to talk about it. I won't demonstrate it, but we'll talk a bit about what it means, what it implies. E is the energy of a given object, m is its mass, and c is the speed of light in vacuum. What this tells us is that, basically, mass is just another form of energy. So you can create mass by using some energy to do it, and you can also destroy mass and get some energy out of it. So most of the mass you have of the objects around you, you may have heard about the measurement of Higgs boson. I think it was back in 2012 or 14, sometime those years, which was heralded as the explanation for the mass of particles. This is not quite true. It explains the mass of some given particles, but in general, the mass of the object around you comes from the energy that was needed to create the particles that make them. So energy can be condensed to make some new particles with a given mass. And this is what is used, for instance, in the huge particle colliders, for instance, at CERN, at the boundary between Switzerland and France, in which particles are going in circles very, very fast, attain very, very fast speeds, and gain a very high kinetic energy, are made to collide with each other. They release a whole bunch of energy, which then condenses into particles, which are then studied. This is why it is a pretty huge window to study the fundamental physics of particles, because we can actually create them and study particles that are very rare, in nature otherwise. So we can create particles based on this. However, we do not create only particles whenever energy condenses into mass. If we can turn some given form of energy into mass, which is another form of energy, we have to be able to do the reverse in order for the energy to be conserved, not for all of it to become mass and becoming useless. So whenever some particle is created, another one is created, its equivalent, which we call an anti-particle, which is a particle of antimatter. Antimatter is kind of like the mirror of matter, which is what we are used to live in, with a few interesting properties. First, each and every particle of matter that you know, a proton, a neutron, an electron, has an equivalent of antimatter. For instance, we'll have to introduce later on the one for the electron, which is the positron. The other we lacked a bit of imagination for the proton. This is the antiproton. For the neutron, this is the antineutron. These have the same mass as their matter counterparts, but have the opposite charge. For instance, an antiproton is negatively charged, but with the mass of a proton, and a positron is positively charged, but with the mass of an electron. And whenever two associated particle and antiparticles encounter one another, they destroy each other. We say they annihilate each other and give back the energy that was used in order to create them. So it is the inverse of energy condensating. It is two particles destroying each other to give back the energy that was necessary to create them. But the energy that is used to bind the different nucleons in a nucleus is based on this principle. It will be some previous mass of the constituents, which is instead used to bind the nucleons together. You can also interpret it as, well, you have some total energy due to the mass of the constituent. The potential energy needed to bind these together has to be negative, so the total sum will be a little bit lower than what you will have just by adding the mass of the constituents. So we'll define the binding energy as EB, as being how much mass we lack between the sum of the constituents and the mass of the actual nucleus, times the speed of light squared. This we'll call the mass defect. So we always compare here the mass of all the constituents. So let's say we have some given atom, which we take as neutral, with Z protons, Z electrons for it to be neutral, and N neutrons. The constituents, we have Z times the mass of an electron plus Z times the mass of a proton plus N times the mass of a neutron. And then we compare what we have with the actual atom. We have the mass of its nucleus and the mass of its electron around it. Usually, what we have in literature are not the mass of the nuclei themselves, but the mass of neutral atoms, which is why we combine this. Instead of canceling this with this, we'll combine the mass of the nucleus and the mass of the electrons to give the mass of the neutral atom, and we'll combine all of these in two terms as well. The neutrons will stay by themselves, but if you have one proton and one electron, this is an hydrogen atom. So if you have Z electrons and Z protons, you have Z hydrogen atoms. You will be able to find the mass defect by knowing the mass of hydrogen, the mass of a neutron, and the mass of the given atom we are interested in. So these masses, you have some tables. I think I listed them in the next slide in your textbook. Sometimes they could also be listed directly in the exercise. Also, I put up on layout a table of a few atomic masses, which might be useful in order to solve the exercises. All masses generally in literature are listed as multiple of a quantity we call the atomic mass unit, small u. You might also have introduced it as Daltons, dA. This is the same thing. So since the masses are very, very small, instead of always expressing them in kilograms and having abysmal numbers, we write them as a multiple of u, which is this mass, which is defined as 1/12 of the mass of carbon-12. So here, I didn't put the 6 at the bottom, but this is carbon-12. So quantity, which will often appear as we'll see in the example, will be u times the c squared we had at the end. So generally, we just factor all the u's outside and get this number, which we have a given value for it, we already pre-multiply all the numbers to get a value of 931.5 mega electron volts, mega being 10 to the power 6. So here you have, there's some tables that can be useful to you. At the bottom of a given page, page 1441, you also have the masses, both in kilograms and in multiples of U, of the proton, the neutron, and the electron. Sometimes also, so EB was the total binding energy of a nucleus. What is sometimes used to measure how stable a nucleus is the binding energy per nucleon in it. So here it is, the average binding energy per nucleon. So we just took the binding energy EB and divided it by 8, the number of nucleons inside of the nucleus. Not more complicated than that. And this depends on the particular nucleus, since the mass depends on it, and also the number of nucleons also. So depending on the nucleus you are taking a look at, this binding energy per nucleon will vary. You have a curve that looks like this, where here you have very light nuclei, such as hydrogen with a single, with just a proton, with one neutron in addition to the proton, and getting to heavier and heavier nuclei, up to iron, and then towards very heavy ones such as uranium, radium, and so on. And what we'll see is this curve does not keep increasing nor keep decreasing. It has a maximum located around iron. So whenever you get around this part, around iron 56, so with 56 nucleons, these are pretty much the most stable nuclei in the whole universe. This will have a consequence later on when we will talk about fission and fusion. These are pretty much the most stable. They have the highest binding energy per nucleon inside of the nucleus. So the moral to get out of this, not all nuclei are as stable. Some are more than others. Some are more than others. So this is a graph based on a few common nuclei. We can also look at another type of chart, which is a bit ugly to take a look at, but we'll just take it slowly. We have on this axis n, the number of neutrons in a given nucleus, z, the number of protons in a given nucleus. And each little square on the graph represents a possibility for a nucleus with a given z and a given n, so a given number of protons and a given number of neutrons. And what you have is a color scheme of how much time it takes for the nucleus to decay, to destroy into something else, destroy itself to something else. Whenever the color is towards the black and dark red, it tends to be very stable. It takes a very long time for it to decay. And when it is more toward the blues, light blues, it takes a lot less time for it to decay into something else. So the fastest it decays, the less stable it is. The lower the energy, the binding energy per nucleon was for this nucleus. And we observe here a kind of line, a kind of pattern with more black than anything else. We have some parts, some configurations which will tend to be very stable, and outside of it, it quickly degrades into yellows and blues and even white, which is pretty short, 10 to minus 8 seconds. Whenever a nucleus decays, whenever it gets destroyed, its goal, as every particle in the universe, is to get a lower energy, to get more stable. So it will decay in order to reach a more stable configuration. For instance, this configuration, this blue square, would tend to decay. towards the bottom to the dark line. A nucleus located over here would try to decay again by reaching the dark line above. They try to reach this heaven, this stable configuration, which will, as stated, will be through a decay, of which we'll introduce a few forms tomorrow. So this was more or less the introduction of what we'll see tomorrow. But for now, basically, a nucleus has protons and neutrons out of it. They are bound together through a binding energy, which which can be expressed through how much mass is missing from the nucleus compared to what it should have by just adding the masses of its components. So on this, would you have some question, some comment? So, given the time, I have another class at 10, and these days I need a little bit more time than usual to prepare. I'd stop here for today. Tomorrow, we'll start off with an example of how to find the binding energy of a given nucleus, and then from there, continue to talk about the different type of decays and how to, we'll find also the energies associated with them. So if you don't have some question or comment, something to add for now, I'd uh, I'd close today's class. Cool. All right. So have a nice day, and I'll see you tomorrow.